Hello, hello. I'm just gonna make sure that everything is set up. Uh, Hello and welcome to the stream. I'm just gonna set up the docs I have here for the chat. Let's see, there we go. YouTube chat. Hello, buddy. How are you? Let's see. I think that was the chats. I'm happy to hear. I'm happy to hear. How's your project going? Hello, Karim. How are you doing? All right, go ahead. Yeah, that's great to hear, Mr. Yes. Have you progressed further? Implemented some new stuff that I need to see? Yeah, you should probably do some shooting, shouldn't you? Or have you already done that? Yeah, you could make it so that you can shoot the physics boxes that you have implemented. That would be pretty awesome. Shooting the boxes, making stuff fly around. Then you could add sound to it, and you would already have a sort of game. Oh, okay. Good luck with what you're gonna do, and thanks for dropping by. Well, cube maps dynamically created are very expensive, especially if you interweave them with geometry draw calls. Uh, so I think the way that cube maps are generated are that they are generated with the GPU but offline, and then saved to file, which gets loaded at load time. For instance, you bake, as it's called, cube maps for an entire scene and save them to file, and then whenever you load your level or your um, what whatever you're loading, you load the cube maps and make sure that the graphics API can access them and sample from them during runtime. You shouldn't do any computations or loading at runtime. I think you should do it at load time if anywhere, and you should use the GPU to bake them if you want performant stuff. You can do runtime dynamic cube maps. I do dynamic cube maps in this project here just for fun. I'm not sure I'm gonna use it, but I have implemented dynamically. You should bake them with the GPU if they are created from your graphics stuff. I don't think you should use the CPU to bake them. You mean compress them or convert them into binary. Well, it's hard to say. You could use RenderDoc, this program here, to actually see what they do, how they generate the cube maps. RenderDoc will, if you run GTA 5 and capture a frame in RenderDoc from GTA 5, you can see how they do their dynamic cube maps. Usually, if you want, yeah, but that's why you do it offline. You bake them with the GPU. So for instance, let me show you an example here. So this lights up here. Let me see. Let me find the right buttons here. So this lights up here is a point light that creates dynamic cube maps. But I could, whenever I create the cube map, instead of creating it each frame by doing draw calls, I could save it to file and then load it, and then it would never need to change unless I change something in the scene. That is called baking, which is actually done by the GPU and then saved to file. Yes, you can. Of course you can save them to file. No, I don't have a tutorial for it yet. I'm sorry, but you can always save your data. It doesn't matter if it's on the CPU or GPU. You just need to pull it out. I mean, um, for instance, in DirectX 12, yeah, there are methods for creating resources that the CPU can read from efficiently. I think it's called the read back heap DirectX. Here's a Microsoft article about it for DirectX 12. As far as I know, you use OpenGL, right? Yeah, you should simply bake them, save them to file, and then load them whenever you need to. before you start your game or your scene or whatever. You load them, and then the engine just samples from them on the GPU. Um, so if you have lights that don't move, for instance, or you have objects that don't move, you can yeah, but the actual cube map is generated on the GPU, you know, right? Well, you probably don't have to, but maybe I'm not understanding what you're trying to do correctly. Yeah, you could do that. Mm, um, I'm not sure. Uh, are you talking about loading a cube map that you already have on disk and using it? Or are you talking about creating a new cube map on during runtime and saving that to disk? Ah, okay. Yeah, you can do that with the CPU, of course. That's fine. And then you just sample it on the GPU. But you shouldn't do it during runtime unless you're doing streaming stuff. If you're doing data streaming, well, you will be fine, but and when I say load time, I mean initialization time. You can preload them. But of course, if you're doing streaming of data from file during your application runtime, you probably have systems for handling that. Um, but yeah, use the CPU to load it from file. Yeah, I think so. Mm, mm, yeah, I think so. If I understand it correctly, you want to load a HDR cube map from file, and you want to use that inside OpenGL, right? Yeah, that sounds reasonable. Yeah. That sounds reasonable. Just do it like you already planned out. Uh, no, it's fine, man. I'm just chilling anyway. I'm really tired, so it's no problem. We could do that. That would be yeah, that would probably be fun, but I'm not sure I can explain everything. I don't know, maybe a textures folder or something like that. It's really your choice, I think, in terms of your whole application structure. Maybe you want to store them together with models or something else. Um, I actually don't know how Unity does it. I think it's just some sort of binary file, assets file with a custom format. It's basically just a field of data. Maybe they do some compression or something, but yeah, I don't know. It probably depends on the map. I don't think there's a totally right way of doing it. It's your application, so you can do how you like in terms of file storage. It's mostly because people do when a game developer does their own engine, they do custom formats and file storage systems. It's part of doing game engines. They're always custom because you never know which format you want on your cube maps. You could have um, yeah, different properties and yeah, it's basically like storing images. I mean, uh, yeah, like raw bitmaps. So usually the developer decides on how to implement file storage and loading for their engine, if that makes sense. My file system is very simple. My levels are just text. They're not even binary because yeah, I haven't prioritized doing any smart file system since I know I will change the engine a couple of times during development anyway. So yeah, you could do that. Usually, yeah, you would make tools for that. Also, if you want to edit the cube maps, you could implement that in a tool. No problem, man. No problem. You could even do command line prompts or command line stuff to do the baking for you, unless you want some visual feedback. All right. To anyone who just tuned in, I had some spare time the last few days, and therefore I actually ended up implementing the omnidirectional cube mapping. So that means that we now have point lights that cast shadows. Have you implemented shadow maps? Yeah, well, my implementation is not so elegant right now, but yeah, I'll optimize it down the road. I think right now I just wanted to show how to implement it on a basic level, and then we will do a more robust pipeline. I think something like cascaded shadow maps that scale with the frustum depth would probably be the way to go. But yeah, no problem, man. No problem, man. I'm just happy to be able to help a bit. All right, so yeah, I just wanted to actually move the lights here. Let's see. Yeah, so as a proof of concept here. Let's see. Let me just move the lights backwards into the scene here. All right. So the lights is pretty big, and I moved it to here. And as you can see, the stuff here cast shadows. Uh, this shadow is different from this one since it's closer to this object here. Also, if I swap the camera and uh, show you, as you can see here, everything casts dynamic shadows. They are not PCF filtered right now, so they are not as pretty and will probably have a bit of aliasing, but yeah. Um, yeah, we just wanted, I just wanted to get it all working. So as you can see, the objects even cast shadows on each other. Yeah, so everything is pretty great here. So the dynamic cube map is right now generated in a not so optimal way, but uh, yeah, generally when you do dynamic cube maps, you want to do culling because um, yeah, shadow mapping in general is pretty expensive because if you do it non-optimized, you end up drawing a lot of geometry into a uh, yeah, what do you call it? You end up drawing a lot of geometry that is not needed to be drawn in order to generate your shadow maps. So generally, in order to do shadow passes, we bind the specific pipelines here. We bind the the cube mapping here, and we make sure that we bind our cubed depth buffer, and I made some changes to the resource allocation / description earlier. So yeah, we of course clear it since it's dynamic, and then as you can see, the expensive part is that we right now render our whole scene geometry just to generate this dynamic cube map. So that's pretty expensive. Also, the cube map has a resolution of 1024 times 1024 per face of this cube. So that means 6 times 1000 times 1000 approximately. So yeah, that's pretty expensive, and we do a lot of draw calls that are basically not needed. The idea would be to create a bounding sphere for the lights. This is point lights, and do some sort of culling of geometry that's outside that bounding volume, and only render those. So instead of doing all our draw calls, we would only do whatever is in range of the lights. For instance, these two objects here maybe, and maybe these objects and the floor, or whatever we could imagine was inside the reach of this lights here. Right now we draw everything in order to generate the cube map, and that's not efficient. Yeah, so in general, that's the way it goes with all rendering. You want to cull as much as you can, either in terms of view frustum, or rather camera frustum culling, as it's called, where you cull objects that are not visible for the camera to see, and that have no meaningful impact on shadows or whatever. You simply cull that, and make sure you do not do draw calls for those parts of the scene, because you can't see them anyway, and that's a way to performance optimize, because the CPU doesn't have to spend time actually submitting all these draw calls, which is really expensive actually for the CPU to do. The GPU usually ends up realizing fairly early that it's not supposed to draw all of the geometry, so it never really draws all the geometry whenever it's outside the frustum of either the camera or the lights that we use for shadow mapping. But it will spend some compute time on the draw calls nonetheless, so it's of course way faster never to submit the draw call at all. Yeah, so that's an obvious optimization, and since we're doing shadow mapping by omnidirectional shadow mapping for point lights here, we can simply call in terms of distance to the lights. All right, so that's our dynamic cube mapping here. Of course, we have the old regular shadow mapping pass here. Actually, I do not transition these resources because we have no race conditions right now, so we generally are not that concerned in terms of synchronization points. Also, the resource barriers that are implemented in basic DirectX12 is pretty slow, so generally I like to avoid them. If we're talking extended DirectX12 like DirectX Ultimate or something like that, or the Agility SDK, you could do enhanced buffers and get some more suitable performance in terms of synchronization um, um, and resource control. Yeah, but anyway, I was going to talk about the dynamic cube mapping here. So yeah, I realized when I tried to um, create a view to the cube mapped depth buffer, that when I bound it as a texture 2D array, I couldn't sample it as a cube map. So the benefit of creating a texture cube, as it's called here, is actually that you can use 3D coordinates to sample the cube, and you can actually use world space coordinates to get the proper sampling inside your shaders. So therefore, the cube, or rather the depth buffer, which is actually described down here. Although it's a texture 2D array when it's a depth buffer. Sorry about that, my headset cut out. It's a um, array with 6 textures inside it. Um, when we describe it as a shader resource view, also called a texture, with the properties of a cube, it immediately knows that it has 6 textures and it's supposed to handle it as a cube. So I made that change. The old version was down here, and it gave me a lot of problems in terms of actually sampling the cube map. Yeah. Um, all right, so I changed that. Let's see. Yeah, so next I also, of course, did the shader stuff. You might remember the vertex shader here. I cleaned it up since I only need the world position of whatever vertices we pass in during our draw calls whenever we create our um, dynamic cube map right here. So we of course apply the world transform for each object so that it's scaled, rotated, and translated properly in the world, and we pass that information along to our geometry shader, which takes 3 vertices, also 1 triangle, and renders them on each of the 6 planes um, of our cube map. So for each 6 faces of this cube map here, we take our 3 vertices, which creates a triangle or primitive, and we of course translate that into a view projection space of the actual cube map. We create these on the CPU side. Right now we do it at runtime, but you could of course precompile them and only change them whenever the lights moves or changes properties or something like that. But anyway, we translate into view projection space of the lights for each 6 faces, which means that we take 6 photographs of the scene from the point of view of the lights. Since I'm doing a right-hand sided coordinate system, and DirectX12 is usually a left-handed system, my texture sampling doesn't get right unless I've invert the x coordinates. So that's a change as well. Depending on your coordinate system and setup, you might not need to do this, but I needed to do it. Anyway, we do not have a pixel shader yet for this step. I'm probably not going to implement it since it will only be used to do transparent stuff or stuff with at least partial transparency, where you do texture sampling in terms of calculating pixels and so forth. So yeah, um, yeah, no pixel shader needed here. That actually does our cube map here. Then let me just show you quickly where I very inefficiently during runtime compile the view matrices for each of the 6 faces of the cube, and I do a single projection matrix because that's always the same. The perspective is always a 90-degree camera with a near and far plane with certain values. Yeah, so we calculate that, and then we calculate the camera angles in terms of the view matrices here. And I do this every frame, but as I've mentioned, you shouldn't do that unless you change your light data. This information here is already bound to our pipeline through our descriptor heap. It's bound in a descriptor table. Let's see. It's actually not bound here, but during our real draw calls here, we bind this descriptor table to our root signature slot number 5, where we actually bind the start of our SRV, UAV, constant buffer, I think, to the descriptor heap. Since the 2 first slots equals the shadow map and the shadow cube map. Yeah, but only bound as texture resources. So we create the descriptors up here during initialization time. This is, as you can see, slot number 2 in our descriptor heap, and up here we create slot number 1. So all the magic happens inside our polygon pixel shader, which calculates the final color of each pixel. Yeah, I have messed a bit around with the ambient lighting in the scene just to play around with stuff. And if you remember my episode in terms of the basic shadow mapping for the spotlight slash can also be used for the directional light if you need to. It's the same principle. But anyway, I also created a function here that's a overloaded version of the actual shadow factor that works for point lights, which means it uses cube maps. And as you can see, the regular version of shadow mapping, where you do a single depth buffer as the output, requires some information about each vertex or pixel or whatever inside the light space that we're trying to calculate the shadows for. But the omnidirectional cube mapping here doesn't need that. It only needs the world space position. Remember what I said about cube maps? You can use world space positions to actually sample the cube map. So it also gets the world space position of the lights, and then we pass in the lights projection matrix. So this uses a little oh, we don't need that. A little what do you call it, header here, where we register our samplers here for our cube map and shadow map. I'm not sure they're actually different. Are they? Yes, they are. I think they are. I think it's actually using a wrap method instead of a border method because there are no borders inside the cube map. It's a 360 degree, no, 3-dimensional rotatable texture. So it maps all the way around in the actual texture space in 3D space. Yeah. So no matter how you sample, you will always get a part of the cube map. Anyway, we are of course bind our shadow maps here. I have allocated them both to space number 1. As you can see, since although we only bind one descriptor table here, the system already knows that the first, what am I talking about? I'm talking about this one. Even though we only bind one descriptor table, the descriptor heap has already made clear that there are at least 2 textures inside that descriptor table that maps to these 2 resources here. We of course also updated the root signature to be able to bind these resources. I updated the here is the shadow cube map. The range here. The range is right here. As you can see, we have 2 descriptors inside it. And we allocated to register space 1, and of course start at shader register number 0. All right, so this is the old calculation of the shadow factor, and this is the cube map based one. Yeah. So even though I pass in the projection matrix, which I actually should use down here, right now it's written out directly. So this algorithm here works in terms of trying to sample this 3D, or I shouldn't call it 3D, it's nonsensical, sample the cube map here. In order to know where to sample from in the cube map, we take the world position of whatever vertex or part of the geometry that we want to calculate the shadow factor for. And then we subtract the light position of whatever light we're doing this calculation for, and we get a directional vector from the lights to the world position of whatever object. And that directional vector, no matter the scale of it, no matter or not scale, no matter the magnitude of it, it will allow us to sample our cube map, because that direction is actually the way that the cube map camera, or what do you call it, and the whole thing that built the cube map itself actually was pointing, and therefore you get the direct information from the cube map by looking in that direction, if that makes sense. The directional vector between the vertex and the lights will correspond to whatever got stored in the cube map whenever it got rendered, of course. Maybe that makes more sense or is more clear. Anyway, we take the absolute values of whatever this vector has, and then we know, because we're looking from one face of the cube, we're taking the perspective of one face of this cube, which means that it's one of the 6 directions around the lights that we have sampled from. We have sampled geometry depths from our scene from this position here, but from 6 directions. So that means that the X and Y won't be big. Imagine that yeah, the X and Y coordinates will never be big, but the depth will be very big in comparison, because of the way that the camera works and the way that the cube map is rendered itself. So each face is kind of like rendered with a very, very long depth. And then on the X and Y, if you can imagine a screen like this here, the X and Y will never get as big as the depth itself. It means that whatever I'm looking at, um, we can only go so far to the left and right and the up and down, but the scene could extend for miles and miles and miles or kilometers or whatever you prefer, um, uh, far, far away. So that means that whatever coordinate, no matter which direction we sample, will actually be that camera's depth. So even though things might be rotated a bit or whatever, um, if we kind of like take the perspective of one of these 6 faces of the cube map, whatever has the bigger component will always be the depth. So that means that even though if it's the x coordinate in world space coordinates that is the biggest and not the y and z, um, from the perspective of our cube, um, uh, it will be the depth. So we decide the largest distance, and we know that is our c value slash depth value, and we of course use that to calculate the normalized depth that we want to compare our cube map. What do you call it? Yeah, so this is actually the depth of the actual vertex in world positions that get translated into the cube map coordinate space, you could say projection space. And you can directly compare that value to whatever is sampled inside the cube map in that according direction. So if the cube map contains something that is closer to the plane of this cube map here, or the camera that took the snapshot for the cube map, that side of the cube map, if it's if there's something in the cube map in that depth buffer that is stored that has a depth value that is closer to the actual lights or cube plane itself, we will know that there's something occluding whatever we put in here, whatever the position of this vertex here. So that means that it cannot be lit. Of course, if there's nothing that has a depth value that indicates, of course, inside the cube map here, that indicates that something is occluding the object, it could probably be lit. So we use that comparison depth here of the actual vertex in object space. We translate it into the projection and create a depth that we can compare to whatever we stored in our cube map. And that is actually our shadow factor. I hope that makes sense. If not, feel free to let me know. Yeah, and we know that that controls the shading. So the last step that we actually could do was something like doing a kernel-based sampling um, that would of course be in 3 dimensions instead of 2 dimensions. That is usually used for our cube map, traditional cube map here. But yeah. So that's basically the algorithm, and it, as you saw, works fine. Everything casts shadows dynamically, and the point lights here obviously casts shadows in multiple directions. Whoops. And Whoops, let me see. So yeah, the spotlight only casts directions of course, or shadows in the direction of what do you call it? Yeah, the actual direction it casts its light. Yeah. So that's basically the difference here. It was fun implementing the cube map stuff here. I haven't really divulged a lot into that stuff, so yeah, it was definitely fun to do. Yeah, and from the perspective of the lights here, things are a bit flipped on the x-axis, but yeah, as I've mentioned, that relates to the way the coordinate space of the game is laid out. Yeah, so um, I'm thinking about what to do next, and I don't know if anyone has any interesting topics that they want us to explore here. Um, I think I should follow my own plan here. And of course start a design document and hello buddy. We have done the most of the shadow mapping. We could do optimization or culling, but we will implement culling generally later, so there's no need to modify the pipeline for that. As you can see, the omnidirectional shadow mapping here and the regular shadow mapping does create some um, extra CPU time. So we could either solve that by doing multi-threading or basically doing a bit of culling, or we can just for now ignore it and know that we would probably implement a more generalizable system down the road. So yeah, one thing I know I want to do is do modifications to the physics system. Yeah, you're gonna do a little web development, it seems. Yeah, but I need to do some modifications here. We need robust, yeah, collision detection. We need, first of all, some bounding volume hierarchies. I think I'm not sure it's spelled that way. I was doing all right. And you use those bounding volumes to create a more efficient method for collision detection. We of course need sphere. I already think we have sphere versus sphere, but we also need AABB versus AAB. We also have that one, but let me just type out whatever I need. OBB versus OBB. I don't think I have that one yet. I only have AABB versus OBB. And then of course we need sphere versus ABB, sphere versus OBB, OBB, ABB versus OBB. I think I have that on one already. And we need sphere versus no, do we have them all then? Yeah. All right, so we of course need a algorithm that does that inside our bounding volume hierarchies. We need to create that. Then I need more robust vertex clipping for meshes, for contact point generation. And we also need something large face versus small face. Right now, the system is not that robust. It's simply just only, it only really handles a small face or a corner or edge or whatever of an object that hits a very, very large face. But we would, of course, want to support different sizes of faces, and through the vertex clipping itself, the contact point generation should be as stable as possible. And if you have no idea what I'm talking about, I'm sorry, that's just basic physics engines. I could explain it more in detail, but for instance, let me show you a bit about what I mean. So whenever we have a physics collision here, as you can see, the 4 contact points of Paul here get generated, and actually the mesh is sort of clipped alongside the collision plane here, and we find the 4 most reasonable contact points. But you could do it for the bounding volume itself, which is what I do right here, and I'll probably stick to that. So it clips the appropriate vertices of the contact point here. But what if we had an algorithm that kind of like, if you imagine something very small being under Paul here, that it knew that the contact points weren't out here because the box was really small. So they would be more like inside here. The box would be something like that only fit under his feet here. And that would be a more stable contact point, because outside here it doesn't really make sense that any force should be applied to Paul. It would potentially also make him a bit more unstable. So you want your vertex clipping to be able to handle different sized planes, and find the most appropriate contact points on those 2 colliding faces. And you do that by vertex clipping and plane clipping, plane and vertex clipping here. to generate the contact points. So right now the algorithm is pretty simple. It doesn't really do uh, a very good job of doing more complicated clipping, so I need to implement that. Then we need a edge case, no pun intended, that handles edge versus edge collisions, which should be only one contact point. Right now, our collision uh, generation algorithm usually it can create one contact point, but usually it's a corner against a plane or something. Okay, so that's also needed to be done. And then finally, a robust collision resolution system that allows for several dynamic interactions. Right now, we're kind of limited in the scope. The engine itself is scalable, but right now there's only Paul, and we haven't created any interactable um, calculations in terms of what if we took a ball and threw it at Paul. Uh, how would the ball react, and how would Paul react? Uh, Right now we only do static versus dynamic object collision detection and resolution, but we want dynamic versus dynamic interaction uh, computations to happen. So that needs also to be done. So yeah, there's a lot of work to do on the physics engine itself. Yeah, and sometimes I'm gonna need to do some research. So I've been contemplating doing some work off stream, since I think it would be boring just to watch me read up and stuff and contemplate how to do things. And then I should probably just stream if I do some coding or whatever. But let me know how you think. But yeah, that's at least a possibility on what to do over the next weeks. And then we could Thank you, man. Thank you, man. But yeah, if you have any other suggestions, feel free to let me know on what to do here on the stream. I mean, otherwise I'll just do whatever. Yeah, I hadn't really planned a lot more for today's stream, so yeah. Let's see. I've been talking for about an hour. I think that's pretty alright. I, I always end up getting a lot of different ideas that I want to do in terms of I've been studying mesh shaders and how they probably do the nanite system in Unreal Engine. Uh, and yeah, I think mesh shaders and GPU calling is a very, very interesting topic. It also makes for more streamlined pipelines, but it's probably harder to do efficiently. Um, yeah, but that's a whole other direction, and I'm probably not gonna take that this project in that direction. Maybe I'll do a separate project offline and simply do a bit of videos on updating on that. That would also solve the problem of me having to do some. Yeah, I guess it wouldn't really solve the problem of me having to do some studying in between um, work sessions on this engine here, but yeah, it would of course give me something to poke at whenever I end up feeling a bit tired or yeah, overworked. Anyway, um, yeah, maybe that was just it for today. A short update on the shadow mapping. Yeah, short but quick. Short but quick. Short but good stream, I meant. Thanks to everyone who dropped by today. Said hi, interacted, asked interesting questions. I'll probably do some streaming during the weekend where I'll work on the physics engine, and then we will be dead set on something very, very interesting, which will be actually creating a game, not only an engine. Um, yeah, so I'm definitely looking forward to being done with most of the systems, um, at least for now, and until we encounter bugs. Um, if you found any of this helpful, inspirational, or just entertaining, or if you feel like supporting the channel or my endeavors, please consider liking, subscribing, commenting, or even supporting in other ways you deem appropriate. Um, I try my best to do follow-up episodes whenever I've done things offline, and try to give a glimpse of how I try to do things and what the different considerations are. But yeah, I do like to make content that is helpful, as well as it's um, something that drives my own endeavor forward. So yeah, feel free to drop a comment if you have any thoughts about that. Anyway, much love to all the supporters of the channel. As Mr. Yes here mentioned on the stream, it's amazing that we're almost at 300 subs, and it's basically been over the last few months. Uh, so I'm really grateful for you guys' support and interactions. So yeah, I hope it continues, and if uh, if yeah, if you have any feedback, feel free to let me know. Okay, I think that was it for today. So please take care, everyone, and hopefully I'll be seeing you around. Much love.